Hello everyone. Today I'm going to discuss about Birch reduction. So before we go into the actual discussion process, I will explain you what is Birch reduction, what is a general reaction, followed by the mechanism of Birch reduction reaction. Okay. So first we will see what is a definition for Birch reduction. So Birch reduction is nothing but reduction of aromatic rings by means of alkali metals such as sodium or potassium or lithium in presence of liquid ammonia and ethanol to give unconjugated dienes. Okay. So in simple way, if you want to understand what is Birch reduction, so reduction of aromatic rings by means of alkali metals such as sodium, potassium, lithium in the presence of liquid ammonia and ethanol to give unconjugated dienes. So here ethanol is going to act as a proton donor. Okay. So the main purpose of using ethanol in Birch reduction, it works as a proton donor. It will donate some protons or hydrogen atoms. Okay. Now, if you see the general reaction for Birch reduction, so this is performed in the presence of sodium dissolved in liquid ammonia, and ethanol can be used as an proton donor. So you're going to get some unconjugated dienes. Okay. Now, generally here, R is nothing but electron donating or electron withdrawing groups. Okay. So, you know, the most commonly used electron donating groups, you can say methoxy, hydroxyl group, amines, NH2, etc. All these are electron donating groups. Coming to electron withdrawing groups, you can have carboxylic acid, okay, nitro group, halogens, etc. All these are electron withdrawing in nature. What I mean to say is, when you substitute an electron withdrawing group on the aromatic ring, the so-called product, you are going to get an unconjugated diene, and moreover, the hydrogen atoms are added at third and sixth position. So at third and sixth position, okay, hydrogens are added. Okay, whereas if the aromatic ring is substituted with electron withdrawing group like nitro, carboxylic acid, or halogen. Okay, so the substitution pattern of the double bonds will be slightly different. Okay, so at first and fourth position, 1, 4 position, the hydrogen atoms are added. This is a difference. Okay, so Birch reduction is nothing but reduction of aromatic rings. Reduction is nothing but addition of hydrogens, or you can say removal of oxygen atoms. Okay, so reduction of aromatic rings you are going to carry out in the presence of alkali metals like sodium, potassium, lithium, dissolved in liquid ammonia, and ethanol. Ethanol is going to act as a proton donor. The final product will be unconjugated diene. But if you see the reaction of Birch reduction, so I have mentioned R. Here R stands for electron donating or electron withdrawing group. Suppose if it is an electron, if R is an electron donating group, at third and sixth position, okay, hydrogen atoms are added. Whereas if R is an electron withdrawing group, at first and fourth position, the hydrogen atoms are added. Okay, so I hope it is clear with the definition of Birch reduction and the general reaction. Okay, now we will see what are the important limitations of Birch reduction, because you cannot apply Birch reduction for all the aromatic compounds. Okay, so there are few examples or exceptional cases where you cannot apply this Birch reduction, which is a major limitation of this one. Okay, so coming to the limitation or drawback. So phenols and isolated double bonds are not reduced by Birch reduction. This point, please make a note of it. Okay, phenols and isolated double bonds are not reduced by Birch reduction. So if you want to reduce those type of compounds, we may go for another type of method. Okay, but this is a major limitation of Birch reduction. Birch reduction cannot be applied for phenols and isolated double bonds. Okay, now we will switch over to the mechanism of action of Birch reduction. Okay, how this reduction process is going to happen and how the hydrogen atoms are going to add on the aromatic ring system. Okay, now mechanism of Birch reduction. Right. So the mechanism is very, simple and easy to understand. So we will take one aromatic compound. The best example, well-known example is benzene, right? Right. So I took benzene. Now I will take sodium, which is an alkali metal. So initially what happens, the sodium will transfer a single electron towards this aromatic ring. Therefore, the rearrangement of double bonds will take place in this way. Okay, so you are going to get so if the double bond is shifted, there will be hydrogen atom here with one single electron. Where from you're getting this single electron? From sodium. Okay. Now, when I shift this double bond to the next position, you will get a double bond here. Okay. And this double bond has been shifted here. So I will represent it by a negative charge. And as usual, the same double bond I have written here. Okay. So the next one is proton transfer. So this proton transfer, it takes place in the presence of alcohol. The general formula for alcohol is ROH. Okay. So when you compare the electronegativity of oxygen and hydrogen, hydrogen is least electronegative. So you can designate by a positive charge. So this positively charged hydrogen will be migrated towards this negative charge so that this carbon atom will form a new bond with hydrogen. Okay, so that you are going to get a free radical like this. Okay, so here you are getting one extra hydrogen atom. So alcohol is a proton donor. Okay, so the hydrogen atom will be migrated towards this negative charge. So negative charge implies that it is having electrons. So when these electrons are taken up by hydrogen, it can form a new sigma bond with the carbon atom of the ring structure. Okay, so this is called as a free radical. And this is radical anion. Okay, I hope this is clear up to here. So the next step again, it reacts with another sodium. Okay. So far it is having only one electron. Okay, so this sodium is going to donate another electron here to get a negative charge. Okay, so because when you have a pair of electrons, it is easy to form a bond. So with single electron, bond formation does not take place. Okay, so you are using another sodium atom here. It will be donating another electron. Okay, already one single electron is present here. So these two electrons will make up a negative charge. So to form an anion, again, this will react with alcohol where hydrogen is having positive charge. So this electrons, when it donates for hydrogen atom, okay, you are going to get a new sigma bond here with another hydrogen atom. Okay, so this is called as 1,4 unconjugated diene, which is the final product of your Birch reduction. Okay, so the mechanism is very simple. So you are using sodium, it will transfer single electron to form a radical anion. The next step will be proton transfer in the presence of alcohol. The hydrogen atom will be migrated towards this negative charge to form a new sigma bond between the carbon and hydrogen, which is a free radical. And remember, these free radicals are highly reactive. Okay, so they can react with another sodium. So this sodium can transfer another single electron to form a negative charge. Okay, so in the last step, again, what is happening? Proton transfer is going to take place where the electrons will be migrated towards the positively charged hydrogen to form a new sigma bond with the carbon atom and hydrogen. So this is called as 1,4 unconjugated, okay, diene. So this is a simple mechanism of action of mechanism for Birch reduction. Okay, thank you.